In the next subsection, we'll look at some little primitive building blocks for parallel algorithms that turn out useful in a variety of applications, and we will use them for parallel sorting, but they are more general than that indeed. And so by themselves, the problems that we'll see in the next few slides might look a bit uninteresting or esoteric, but bear with me for a bit. We'll come back to them, and they naturally fit into the problems that we will identify for parallelizing sorting methods. The first of these problems is called the prefix sum problem. And so it's a very simple problem. You're given a list of numbers or an array of numbers, and you're supposed to find all the prefix sums. Well, that's just using the name again, summing up the first I elements for every I. And it's okay if we do this in place. So you could think of it as we start with this array, and we want to end up with that array, where the idea is that every entry here contains now the sum of the entries up to this point, including that point. So the last entry will always contain the sum of the entire array. The first entry will always just be the first entry from before. If we have zeros in the array before, then we'll have a run of the same entry. All right, so that's some simple observations about this problem. Again, forget about for the moment why this is an interesting problem. Just assume we want to solve it. What can we do to solve it? Before we start with parallel algorithms, let's see what is the baseline that we compete against. What's the best sequential method? Yep. And I'm not asking about a complicated algorithm. Essentially, the simple, straightforward solution gives you the running time I'm after here. Let's wait for at least 60, maybe. The votes are trickling in. Three more, two more. Oh, wow, it jumped. Okay, there you go. We had votes for various options. You can actually do this pretty fast. You can do it in linear time, which means that's the time to just read the entire array. Okay, how do you do this? Here's the code. It's a very short code. The main trick is just if you want to find the sum up to including the ith element, if you already have the sum up to including the one before, then there's only one more element that you need to add in. So sequentially, you can do it like this. You iterate over I, and then you just do one summation in each step. You start with just the first two elements, then you add one more into the sum of the first two. That gives you the sum of the first three, and so on and so forth. So we can do it with n-1 additions and linear time overall. Of course, the problem is that that's maximally data dependent. I always need for the next step in the computation, I need the result of what I've just done. That's the antithesis of parallelization. So that won't work. But we can still take this algorithm as inspiration. And it's insightful, and it just gives the easier to draw pictures if we focus on a subproblem, namely summing up the array. Now that sounds like we're reaching problems that are so simple. What can you really do interesting with just summing n numbers? Now, if you look at this from the perspective of what additions are done, if you need to sum n numbers up and all you can do is add 2 numbers at a time, you will always need n-1 additions. No way around it. Each step takes 1 number away. But of course, you can choose which numbers you add up and in what order. And this happens to be a binary tree because it's a binary iteration, a binary operation, and you have 2 things that you add up. So the sequential algorithm corresponds to this kind of tree. We start with the first 2, and then we add in the third, and so on. Yeah, forgive me that I didn't start with 0. I'm offending myself here with not being consistent. But yeah, imagine there's a 0, that's a 1. So that aside, that tree is useful for this algorithm, but it has this maximal height, right? We've seen the same kind of tree as the worst case for binary search trees. Of course, I can do better. If I want to minimize the height, I can use a more balanced tree. And now instead of 1, 2, 3, 4, 5, 6, 7 steps that all have to wait for the previous one, I just have 3, height 3. So can we somehow use that also for the prefix sum problem? It also seems if you want to compute the sum of n numbers in that way, there's no way to get below the height of such a tree. At least unless you can do something else than adding 2 numbers at a time, that's the best you can do. Well, but for the simple problem of just summing things up, you can also write this as a proper algorithm that operates on the tree level by level up. So it first executes all those additions, then those, then those. So the parallel time, the span of that algorithm will be the height of the tree. And you can do the exact same thing for the prefix sum problem by just doing all the trees in parallel. That sounds wilder than it is, but it actually has a nice regular structure. So what we'll do is we do the lowest level of the trees. And if you look at what the lowest levels do, they just add up consecutive elements. So the first step adds up consecutive elements. So every element now contains the sum of itself and its left neighbor. In the next step, you do roughly the same, but you jump by 2. So this guy, for example, now contains the sum of these 2. And each of these, remember, was the sum of the 2 neighbors here. So it turns out that this now contains the sum of these last 4 elements. And the same thing is true for all of the others with a few boundary conditions at the beginning. But every element now contains the sum of the 4 elements before it. And guess what? We just keep going like this by doubling how far we jump back. So here we jump back 4 positions, and then we have summed up 8 elements. And if we do this here, we need 1 more round. And now each of these elements in the last round, after the last round, essentially contains a full binary tree of everything to the left of it. And here's the one example highlighted, but it's true for all of those. That's what I meant by doing all the binary trees in parallel. We're not doing them in parallel in the primitive way. We're not recomputing results that they share. We only recompute the results once. That's what's meant by this. By doing this in these rounds, level by level, you automatically avoid any redundant computation. Okay? I think at the level of these pictures, the algorithm is fairly straightforward to understand. And it's quite clear why it works, because every element exactly shows you what it has summed up. In code, it's a little it's a little more annoying because you have to do the computations of the indices, but it's the very same idea. So you can do this. I guess that's maybe, it doesn't give this nice animation or this nice picture, but to do this step, I only need the previous round step. So I can each time overwrite the array that I'm using. I don't need to keep the old results around. The old rounds can be overwritten. That's that remark. And here comes, for the first time, a property of the model, of the PRAM model, that is somewhere between a bit idealistic or convenient or an idiosyncrasy of the theory. Call it what you want. That's a part that's not so realistic. So if you wanted to implement this, you would have to do that explicitly. But because we're working on the PRAM, everything works in lockstep. So when I do one round of writing to the array, and then the next round reads elements, I can rely on all the writes going through before any of the reads start. Everything's nicely ordered. I do one step after the other. That's the part where on current architectures, you would have to explicitly synchronize the different threads. If you program with threads in a programming language, they run at different speeds at different times. The operating system is even free to schedule them, like pause any one of them for an indefinite amount of time and then wake it up again. So there you would have to explicitly say, now we'll wait for everyone to write their round results and then continue. What we see increasingly is that this kind of abstraction or this synchronization is done in software as part of the programming framework that you're using. And so it's getting less and less of a problem. But the hardware essentially doesn't support it in exactly that way. Anyways, here's the code. It's the same as before. It's just doing this with proper index arithmetic. Nothing complicated going on other than that. The overall number of rounds is, well, the depth of such a binary tree. So it shouldn't surprise you that there's a logarithm involved. And it turns out to be just log base 2 rounded up is enough. Then you compute the step size that doubles in each step. And here's what we actually do in parallel. So the rounds are sequential. I have to do one round after the other. But in each round across the array, I can work in parallel. And what I do in parallel is just a single addition, and then I write it back. So note that I've split this operation into 2 time steps here. And that's depends a bit how your pseudocode is defined. But this makes it explicit that we first read the old results, compute the new results, and then in the second step, we write the result back to the array. That's my way of making this a bit more explicit. You could maybe you're tempted to write this in one line, but you have to keep in mind that it's actually several steps on any hardware that I know of. Okay, otherwise simple code. And this would run reasonably fast. So how fast exactly? In one round, all these additions here, it's constant time because I'm just doing a bunch of additions and reads and writes. And I do all of this in parallel. So in terms of span, this entire loop is constant time, constant span. And constant times the number of rounds gives you the overall span. We have logarithmic number of rounds. So that's log n span overall. That turns out to be best possible depending on the model, but if you have to sum up n numbers and all you can do is these binary additions, that's the tree argument again. Even if just your task is to compute the sum of the numbers, you can't really be better than that unless your model allows weird operations. But let's look at the work as well. The analysis here is essentially the same. You have constant for each inner loop iteration. But for work, analysis for work is essentially ignoring all in parallels. For these loops, at least, that's exactly what happens. Instead of doing them in parallel, we have to sum them up. So this was order 1 work, but order order 1 span, but order n work for each of these rounds. And we have logarithmic being many rounds. So the overall work is order n log n. Remember we said we can do prefix sums sequentially in linear time. So our algorithm is not work efficient. It is still a good algorithm because it's low overhead. It's just a logarithmic factor worse in work. So it might, even for a relatively decent number, a reasonable number of processors, give you a speed up. But at least theoretically, we can ask whether we can do better. So it's overall good. We get a speed up. But the question is, can we do even better? So there's, again, a more tricky algorithm that I'm not going to show, where you can do with twice the span, doubling the span, you can get linear work. I instead want to show you something that has 2 benefits. I mean, it's a tiny bit slower. It's 3 times instead of 2 times. But we ignore constants in much of this module anyways. The good thing is it's a bit simpler, and it's more versatile, because again, it uses a blocking trick that is more versatile than this concrete problem. It can be applied in other scenarios as well. So let's have a look at that. The idea is to use what we already know, which is an algorithm that has good span, but slightly too much work. So we want to make use of that algorithm, but apply it to slightly smaller instances and do that in parallel. That's always the idea of this blocking. Try to break things down into slightly smaller subproblems so that you can use the slightly slower algorithm, but do that in parallel so that it overall doesn't hurt. Now, if you just do that and keep repeating the same work, you're not saving the work. So you have to do a slightly smarter thing than that. And that's the problem-specific part. So maybe let me do the example first. And so I'll have to draw that. Let's do a simple example where our array is just all ones. I'll have to draw this a bit nice so it doesn't get too messy. It's not my strength. So suppose we have an array of length 12, and we'll break it into blocks of size 4. That number is basically given in the algorithm. So in our example, we have 12. And now we're using blocks of size log n. So we bunch log n elements together, and here that works out to 4. Oh, that's b. So I'm breaking the array up. Why do I use just ones? Well, if I'm computing the prefix sum, what's the prefix sum of an array that is 1 in every position? It's just the first n integers. So it's nice to check that the example worked out correctly. That's why. But other than that, it's general. If it works for these numbers, it basically works for any other numbers in the same way. Okay, so we broke the problem into blocks. Then for each of the blocks in parallel, we compute the local prefix sums, just in the tiny block. And for that, we use the algorithm we already know. So let's do that first on the example. So I take this as small independent arrays, all filled with ones. If I compute the prefix sums, that's just 1, 2, 3, 4 in all of them. Now, maybe it's good to already note how much time this takes. And we'll have to analyze work and span separately. So we use our we use the fast sequential algorithm for this, not the parallel one at this point. We use the fast sequential algorithm, but do it in parallel for all the blocks. And the sequential algorithm had linear time. So each of these takes order B time. And of course, that's the total span as well for the entire round, because it's run in parallel. But we do n divided b times that in work, because we have to sum for work, we have to sum up over all the blocks. All right, so far so good. Now we use the work inefficient algorithm that we've had before, but not on the entire input, only on the rightmost elements from each block. So I look at this subarray, and I'll draw it in the example just as a really fat array with only 3 entries. But you should think of this only containing that last entry of the small arrays. And I compute the prefix sum of that. So 4, 4, and 4 becomes 4, 8, and 12. So previously was 4, 4, 4. And now it's summed up to that. So how much time does that take? I'm using the parallel but work inefficient algorithm for it. The size of this array is n divided by b, because that's the number of blocks that I have. And remember, the work inefficient algorithm had log n span, but n log n work, not the linear time, linear work. So we have log n prime span and n prime log n prime work. Now if you insert what we know about b is log n. So I could have maybe simplified this here earlier. If we have n divided b times b, that's of course just n. If I have log of n prime, if I insert what I know about n prime, n divided log n, that's log n minus log n. So that's a lower order term. The asymptotic cost here is the same as log n. Span, not spam. And the interesting thing happens here. If I insert n divided log n here, what I get is that the log just cancels. N divided log n times log, and here again I have technically log divided log n, but this divided log n just becomes a minus log n. That's the lower order term that is dominated by the rest, or you can upper bound it by the rest. And what's left is a log n down here and a log n up here that we can cancel. So that turns out to be just order n. And that's where the magic happened. We took a work inefficient algorithm, but we applied it to a slightly smaller problem so that the overall work that it does is small enough. That's what the parameter choice comes from. The way I presented this is basically I showed you the final result and said, haha, this fell from the sky, and that's how you do it. But the way you should approach this if you do it to a new problem is you work backwards. You have an algorithm that doesn't quite get the work right. So you can compute how much you have to thin out the problem so that the work is what you want. And here it's a log factor that you have to lose. Okay, we're still not done with the overall problem. We've just computed these intermediate steps. So what you do in the last part is you add to each block the prefix sum of the rightmost elements, and that gives you, you can do this again, you do it in parallel for each block, but you can do it sequentially within a block. So you take this number and add it to the orange number. So here you take that number and you add the orange numbers. In the first block, you don't really do anything. You take that one and add these. And then you get the final prefix sum from before. So why is this correct? These are the prefix sums within the block. All that's missing to the overall prefix sums is the sum of all the elements before it. And that's that green entry, because it was the sum of this block and the sum of this block and the prefix sum of that. It's layers of prefix sums on top of each other. So how much time do we need for that? We again do this sequentially. And we need order B for each block. The length of the block, we just do B additions. So the span is order B. And the work is, by the same calculation as here, is linear. So if we sum this all up, what do we have for span? We have order B, which is order log n, remember? And we have log n and we have log n. So the span is log n. And what do we have for work? You sum that up too. So we have order n, we have order n, we have order n. So n. Linear work. That's spelled out here in a bit nicer as well, but I thought it's nicer just to do it on the example. So overall, we found now an algorithm that has the same span as what we had before, up to constant factors. But we reduced the work to order n, and that's the best sequential algorithm, because we have to read the array. So we found a work-efficient algorithm now as well. And funnily, it uses both of the previously best algorithms, but combines them in a smart way so that it's better than either of those in isolation, right? The algorithm both uses the fast sequential algorithm and the previously fast but not work-efficient parallel algorithm. But by combining them with blocks of the right size, you get the overall improvement. Whenever I present this, I feel it's kind of surprising how this works. You can take two things that are not optimal and you combine them, and then the result is better than either of them. But yeah, the clever choice of the size of the block is what makes this happen. There's one more such parallel primitive that we'll look at, but that will be much shorter because it's essentially the prefix sums in disguise. But it's one more step towards what we'll need for sorting. So the problem here is called compacting an array. And it has two inputs. It has one array of objects. And it has a bit vector that tells you which of the elements you want to keep, all the ones with a 1. And you're supposed to create an output that consists of just the elements that have a 1 on top, but compacted in an array at consecutive positions. Now, luckily, you don't have to work very hard. You can reuse prefix sums and the clever way of assigning things on the PRAM to solve this with very little code. The way this works is you first call prefix sum on the bit vector. So here I'm making a copy of the bit vector first because we need it later, and remember, prefix sums overwrite their input. But essentially, we compute the prefix sums of the bit vectors. Now, what does that do? It means, for example, the 7 here has an entry above it that's a 1. And if I sum up everything that's up to this point, that's 3. And that's exactly the position in the output array where it should go. So once I've computed the prefix sums, I can use these entries above the elements to know where they should be written to. And so I can do the second part in parallel. For each element in A, I either do nothing, namely if there's a 0 above that element, or I take it and write it to the output to the position that's given by this C, by the prefix sum of all the bit vectors. And that's how I can do compacting. So I'm spending constant effort in each of these inner iterations. Because these are all done in parallel, it's constant span and linear work. That gets too small, I guess. I try to make it a bit bigger. And what we have to add is the cost for the prefix sum. Now, let you do the work. That's the final test if you kept everything in your mind, kept everything in memory. I guess I'll show you the code. The key piece of information is on the slide before that. It's an interesting spread of answers. I'll wait for 60 people again. Okay. There we go. It's a good spread, right? But the majority is right. So to finish off my analysis, I almost gave it away already. What we've just seen about the parallel prefix sum, here it is. We can do it in log n span and linear work. Now the span of this overall thing is dominated by the prefix sum. The rest that comes afterward is essentially nothing, just a constant span. And the work is linear in both parts, so it remains big O of n. So that's the right answer, at least if we use the fancy prefix sum algorithm.